Example 1.2.1 has us looking at a circular puddle that is growing, and the surface area of the puddle is growing at a rate of 4 centimeters squared per hour. We're asked to make sense of the surface area and the radius of the puddle after 84 minutes. So I want to point out a couple of things before we dive into the actual analysis here. First of all, notice the units on this number here. We're talking about the rate of change of the surface area. So in the numerator, we have the units of surface area, and in the denominator, we have the units of time. If we had instead centimeters cubed here per hour, this would suggest a changing volume, and centimeters per hour would suggest a changing position or changing. So I secondly want to emphasize that this problem points out that we're looking at a constant rate. In this course, we'll essentially only look at rates of change that are constant. The major objective of calculus is to be able to work with rates that are changing, but in precalculus we'll focus on constant rates. So what this means is that the puddle is not growing faster and faster and faster as time goes on, and it's not kind of trickling out, it's not slowing down, it's growing at a completely constant rate. And the last thing I want to point out is that this units of minutes here doesn't line up nicely with our units of hours here. So with that in mind, let's dive in. Will we have an easier time modeling the surface area or the radius after 84 minutes? We're working with the surface area, so let's start by computing the surface area and then using that to compute the radius later. So what can I say about the surface area after 84 minutes? Well, I know that each hour the surface area is increasing 4 square centimeters. I can either choose to convert this to hours or this to minutes. Let's change this hours into minutes. So I have 4 centimeters squared per hour. I want to multiply this by some conversion factor to get rid of hours and introduce minutes. Since I have hours in the denominator here, if I want them to disappear, I'll put hours in the numerator. And I want to introduce minutes in the denominator. And I want to make this conversion factor be equal to 1. 1 hour is equal to 60 minutes, so here's my conversion. I have that this surface area is growing at 1/15 of a square centimeter per minute. So with this, it's quite straightforward to compute the surface area. In particular, each minute, the surface area is increasing by 1/15, so after 84 minutes, the surface area will have done that 84 times. Although I did this computation essentially intuitively, you could think of it a little bit more formulaically by thinking of this as the rate of change times the amount of time that passed. So we have this rate times 84 minutes. We find that the minutes will cancel, and we're left with 84/15 centimeters squared. Now, we need to compute the radius. There's a clear relationship between the radius and the surface area. In particular, the surface area is equal to pi r squared. I can divide both sides by pi and then take the square root. And in taking the square root, my units will change from centimeters squared to centimeters. So in the text, they take a slightly different approach. Rather than converting this rate of change into centimeters squared per minute, they decide to convert 84 minutes into hours. The two approaches are quite similar. I hope that you'll be able to make sense of both.